A very good day to the examiner and supervisor. My name is Macalister Ana Alias, and today I will be presenting my final year project entitled Game-Based Learning for Evacuation Awareness in Cultural Spaces. So this project was conducted under the supervision of Madam Hamizan binti Sharbini. It explores how we can use digital simulation to solve real-world safety problems in museum. So let's begin with Chapter 1, Introduction. So, cultural spaces such as museums and galleries are unique public environments. Unlike office buildings or shopping malls, which are designed for efficiency, museums are designed for wandering. They often feature complex, non-linear layouts, narrow corridors, and sublevels. However, this creates a significant conflict between heritage preservation and public safety. In many heritage sites, we cannot simply place large neon exit signs everywhere because it disrupts the historical aesthetic and immersive experience. So, this leads to a dangerous reality in which visitors are navigating complex mazes without a clear safety guidance. If a fire were to break out, the path to safety is not immediately obvious. The next slides would bring us to the core problem, which is not just architectural but psychological. First, we will have the phenomenon of leisure absorption. When people visit a museum, they are there to look at artifacts, so their attention is fully absorbed by the exhibits, meaning they effectively block out peripheral information like safety maps or exit signs. Second, current safety methods are passive. Brochures and static maps rely on the visitor taking the initiative to read them, but most of them do not. Next, in the absence of knowledge, humans exhibit herding behavior. During an emergency, instead of looking for an exit, panicked visitors simply follow the crowd, even if the crowd is running in the wrong direction. So the consequence is a high risk of disorientation and delayed reaction time during the critical first minutes of a fire. Moving on to the aim and objectives. To address this, the aim of my project is to develop a game-based learning system that enhances public preparedness. So I have broken this down into three specific objectives, which is the first one would be to develop a 3D interactive simulation of a cultural space using the Unity engine. Next is to simulate realistic emergency stresses, specifically smoke, alarms, and time pressure, forcing the user to make decisions. And the third one would be to evaluate the system effectiveness by comparing user knowledge before and after playing the game. Moving on to the next slide, which is Chapter 2, Literature Review. So in this chapter, I conducted a comparative analysis of existing solutions to identify the research gap. So as you can see in the figure, the con of experience theory tells us that humans only retain about 10% of what they read, which explains why brochures fail. However, we retain 90% of what we do through active simulation. So here I reviewed three types of existing system, which is the traditional methods like brochures, which are low cost but low engagement. Next would be industrial VR. These are high fidelity simulations used for training firefighters or factory workers. However, they are often too technical and complex for casual tourists. The next one would be emergency apps. These are mostly reactive, tracking users or sending alerts, but they don't teach special awareness. So my project fills the gap by creating a simplified, accessible simulation specifically designed for the cultural context of a museum. So the proposed solution would be a simplified 3D simulation for the museum visitors. Moving on to chapter 3, methodology. I selected the agile methodology for this project. So standard waterfall development doesn't work well for games because gameplay requires constant tuning. I needed to test factors like is the player moving too fast or is the smoke too thick to see. So the figure in the slide is the agile workflow. So my development was broken into three sprints. Sprint 1 focus on the core mechanics such as movement and collision. Sprint 2 introduce the game logic, specifically the fire triggers and health system. And Sprint 3 focus on the user interface and final polish. So for the simulation environment, I created a digital twin of the Borneo Cultures Museum, specifically level 3. So in the figure shown, I chose level 3 because it contains the In Harmony with Nature exhibition. As you can see from the map, this area features open plain zones like the rainforest and coastal areas. It also contains complex structures like the Bidayo Baroque roundhouse. This non-linear layout makes it the perfect testing ground for evacuation training, as the path to the exit is not a straight line. So I will use Blender to model these assets to ensure they match the real-world location. So moving on to the system logic, which is the flowchart. So this flowchart illustrates the core logic of the system, effectively the game loop. So the simulation follows four phases. The first one, initialization, in which the player enters the museum and explores freely. We call this baseline behavior. The next one would be the trigger. So after 60 seconds, the system activates the fire event, smoke particles spawn, and alarm sound. Third one will be the decision logic. This is the most critical part. The system checks the player's posture. So if the player tries to run, standing up while in smoke, their health decreases rapidly. And if the player crouches, which is the safe posture, their health will remain stable. So the last but not least would be the outcome. The game ends either when the player finds the exit or the health reaches zero loss. So moving on to the next slide, which is the mathematical model, or in other words, scoring. To implement the health logic I just described, I use the following formula in the C sharp scripts. So the formula here is H is the player's health, whereas the damage rate is set to 5% per second. So this mathematical model is crucial because it creates urgency. At a rate of 5% damage per second, the player has exactly around 20 seconds of mistake time if they stand in the smoke before they fail the simulation. So this will forces the user to take the crouch mechanic seriously and reinforces the learning outcome. Next is the system architecture. So this class diagram explains the technical architecture behind the simulation. So I utilize an object-oriented approach with three main scripts, which is the game manager. This is the brain of the system. It acts as a singleton, tracking the game state, the global timer, and calculating the final score. So next would be the player controller. This handles user input, which is the WASD keys, or in other words, forward, left, right, and back, and communicates the player stats, crouching versus standing to the game manager. So the third one will be the hazard system. This controls the instantiation of smoke particles and audio triggers. So these modular designs allow the system to be scalable for future updates. So moving on to the user interface design. Here is the design for the simulation. I kept the interface minimal but informative. So as you can see on the top left, you will see the health bar which represents oxygen. It changes colors from green to gray to indicate danger. And at the top center, there will be a timer that adds psychological stress. And at the top right is the minimap. Importantly, I designed the minimap to show the immediate walls but hide distant exits. So in the middle would be something interactive to interact, such as press F to interact when the user or players finds an exit. So this was a deliberate design choice. So if I shot the whole map, the game would be too easy. By limiting the view, I forced the user to look at the 3D environment and search for the real physical signage, mimicking a real emergency. Moving on to the development tools. To build this system, I use the following software stack, which is Unity Engine for physics and rendering, Blender for 3D modeling and the museum assets, and VS Code for C Sharp scripting. So regarding hardware, I optimized the asset to run on a standard Intel Core i3 with 8 gigabytes of RAM. This is important because it ensures the system is accessible. Museums or schools don't need expensive gaming PCs to run this training, so we can work on a standard issued computers. To validate the project, I conducted a pilot study with 30 respondents. So in the figure shown here, which is a pie chart, the demographics provided a very positive insight, which is 76.7% of the respondents indicated they play video games either frequently or sometimes. So this confirms that the audience, the general public, has a high level of digital literacy. So they are already comfortable with game interfaces, which validates that a game-based learning approach is appropriate and accessible for them. So the next slide would be the findings, which is the safety gaps. So this is arguably the most critical slide in my presentation as it quantifies the human behavior problem I mentioned in chapter 1. So the figure shown, which is a bar chart, we asked users about their habits in museums on a scale of 1 to 5. The top bar shows focus on exhibits with a very high mean score of 4.33. This proves the theory of laser absorption, in which visitors are highly distracted, and the bottom bar shows actively look for exits with a low score of 2.67. This huge gap between focusing on art and focusing on safety proves that the current passive methods are failing. Visitors simply do not look for exit on their own. So this data justifies the need for an active intervention like my project. So to conclude, this project successfully bridges the gap between heritage preservation and modern safety training by moving from passive observation, which is brochures, to active experience, gaming. We can help visitors build a cognitive map of the museum exits before an emergency ever occurs. So the expected outcome is a functional prototype that not only educates but also supports SDG 11.4, which is safeguarding the world's cultural heritage. So future work could see this expanded to virtual reality or mobile AR for on-site training. So that concludes my presentation. Thank you very much for your time and attention.